So on the screen in front of you is a uniform magnetic field. I've drawn it uniform because it's simple. What I'm going to talk about is definitely not dependent upon the fact that this field is uniform. I've drawn it like this because it's simple to see. But you have a magnetic field B. You have a charged particle with some Q and some mass, right? And the mass may or may not play a role in what we're doing here, but we have a charged particle. By virtue of being in this universe, this particle has some mass. Not all particles have mass, to be fair, but this one does. And some charge Q. And this particle is moving in the field with some velocity v, such that the velocity vector makes some angle theta with the magnetic field. All right, so in general, theta can range however you want it to, but notice how I'm measuring theta. I'm measuring theta from the velocity to the field. In other words, I'm looking at the velocity vector, and then I'm measuring from the vector to the field. That is actually very, very important. The order of how I measure this angle is going to matter a lot. So I'm going to measure from the velocity vector to the field. But if I do this, if I run this experiment, what I find is that in general, this charged particle feels or experiences a force. I'm going to subscript this with a B. Sometimes you'll see it subscripted with an L for Lorentz, just like you saw the electrical force subscripted with a C for Coulomb. I'm going to subscript it with a B. No big deal. It's just a force. But this charged particle moving in the magnetic field is going to feel a force. And interestingly enough, we can determine experimentally that this force is proportional to the magnitude of the charge, which is probably obvious. Maybe I should say the size of the charge. We'll talk about what happens between negative and positive charges in a little bit, but the force is going to be proportional to the size of the charge. It's going to be proportional to the strength of the field, which also should maybe make some sense, right? We saw the same thing with electrical forces. They're going to be, if I put a charged particle into an electrical field, the force is going to be proportional to the size of the charge and the strength of the field. So nothing has changed here. Although, if you're really paying attention, you might wonder why in the world a charge feels a force from a magnetic field. We'll get there. But it's proportional to the magnitude of the charge, proportional to the magnitude of the field, proportional to the velocity, which is not something anybody expected when we first saw it, but it turns out to be proportional to the speed of the charge. I should do it like this. And really, really, really interestingly, and really, really unexpected if you didn't know what was going on, it's actually proportional not to theta, but to the sine of theta. Move it over so you can see. So the force that this particle is going to feel is proportional to not only the charge, not only the magnetic field, not only the velocity, but it's proportional to the sine of theta. In fact, I've gotten all the proportionalities out of the way. Let me just write down by magnitude what this force is. And I'm not dealing with the vector nature of this yet. I've thrown away all the vector and directional nature from all these terms here. So I'm not dealing with the vector nature yet. This is just by magnitude. I can actually write down force, the magnetic force on this charged particle is equal to QVB sine of theta. And I'm always going to write it like this. I'm always going to write it in this order. That's because if this equation comes out of a very particular way to multiply vectors together, which is not commutative. If you're in a calculus-based course, we're going to investigate that in a different video. If you're in a trig-based or algebra-based course, you don't necessarily have to worry about that, but we are going to take some order into account when we talk about how to determine the direction of this force. which is a little bit more complicated than you might think. So I'm always going to write QVB sine theta. The V and the B are going to appear in this order, even though in this magnitude equation, order shouldn't matter, and it doesn't matter in a magnitude. Multiplication is commutative. But what's going on behind this is a vector multiplication, which is not commutative. So I've got to be really careful. So I'm going to write it like this, and I would encourage you to do the same. This, though, leads to some really interesting situations if I look at some extreme cases. So notice if V is equal to 0, the force felt by the particle is equal to 0. That, I think, is really, really interesting and also just really weird. We're saying if this thing is moving, it feels a force, but if it's sitting still, it doesn't. That's kind of strange. I don't know of anything else that acts like that in the universe. It's unexpected, but unexpected in physics is also interesting. So that's an interesting case. If it's not moving, it feels no force, but the minute it starts moving, it could feel a force. We can also say if theta is equal to 0 degrees or 180 degrees, or if you prefer, 0 or pi, however you prefer to write that, if you prefer degrees or radians. This means the force is 0. So it gets even weirder. If this thing is sitting still, there's no force. If it's moving parallel to the field, which is 0 degrees, or anti-parallel to the field, which is 180 degrees, or pi radians, then there's still no force. I'm hoping that strikes you as strange, because it is strange. So that's where this proportional to sine theta comes in. If theta is 0, the sine of 0 is 0, there's no force. So the particle has to be moving at some non-zero or non-180 degree angle to the field for there to be a force in the first place. Okay? All right. Takes care of all this. And notice also what that means. If theta is equal to 90 degrees or 270 degrees, that force is maximized because it's proportional to sine theta. If the velocity is in the direction of same direction as the pin, the force is 0. If the velocity now is in the direction of the pin, the force is at a maximum, which means there's our gradations as I rotate through that angle. This produces 0 force. This produces just a little force, a little more, a little more, a little more, until finally I reach the maximum of the force here. All right, and we're talking about magnitudes because the sine of this of 90 degrees is 1, the sine of 270 degrees is -1, and so we're going to have to figure out how to deal with the negative signs as well, but at least by magnitude, the magnetic force is maximized when the velocity of the particle forms an angle of 90 degrees or 270 degrees with the magnetic field. Okay. So all of that, I hope, is a little bit surprising, or maybe I hope it's not. That means you've read the text. But at least the first time you saw it, it probably should have been surprising. If it wasn't, you might not have been thinking about it. So there's one more surprising thing, though. To do that, I'm going to have to exercise my three-dimensional drawing skills, which are suspect, but we cannot get away from them. So let me draw a good old XY coordinate system, but from an angle. So the idea is, if this is x and this is y, we're looking at this plane from an angle. And then the reason I want to look at it from an angle is because I'm going to have to make this a three-dimensional coordinate system. So let me put on my z-axis. All right, fair enough. The magnetic force, let me get the right pen here. The magnetic force is exerted at right angles to both the velocity vector and the magnetic field. This might, I think the proportionality to sine theta is maybe the most surprising, but this is a close second if it's not the most. We haven't seen anything like this in any physics class you've taken thus far, which would be physics 1 and half of physics 2. So in all of the situations, the force that is exerted lies in the same direction as the field. Think of gravity. The gravitational field, as long as you're either above the surface of the earth, is up or down from the surface of the earth, and the field is down and the force is down. For electricity, if the field was to the right and you put a positive charged particle in there, it feels a force to the right. If you put a negatively charged particle, it feels a force to the left. But in both of those situations, it's easy to see that it's in the direction of the field. It might be anti-parallel if you have a negative charge, but it's in the same direction. But here, we're at right angles to both V and B. So what that means is if I have a magnetic field that looks like this, where I've drawn this to show you that this is in the x direction, and I've got a velocity which looks like this. Right? This is B, this is V, and the idea here is that these are lying in a plane. They don't have to be at right angles, but I've drawn them. But if they're lying in somewhere in the xy plane here, and what I can say now is that the magnetic force is going to be exerted mutually perpendicular to both of those. It's going to be hard to draw this, but I'll draw this on out. That will be where such that this is a right angle. So it's, like I say, it's hard to draw here, but that's the idea. It's mutually perpendicular to V and B. That is, V and B, no matter if they're, I've drawn them at a right angle, but even if they're not, I can always form a plane using these two vectors. The force that is exerted then on the charged particle will lie mutually perpendicular to that plane. That's really, really interesting. What that means, of course, think about it, and we're gonna go back to physics 1 here for just a little bit. There is a force exerted on a particle that is always, always, always perpendicular to the velocity of the particle. So, of course, if this is free to accelerate in the direction of the force, it will do so. But as soon as it accelerates, that means the velocity vector will change slightly. But then, because the force is always perpendicular to the velocity, the force will change as well. So you can just pick out a couple of situations there. We'll go back to looking at the plane of the paper. If the velocity of the particle looks like this, and I'm not going to draw the B field, and I find that the force looks like this, then if the velocity moves, or let's say if the particle turns, maybe later the velocity will look like this, but the force has also turned to maintain its orthogonality. So a little bit later, this will occur. So no matter how the velocity vector turns, because of the way the magnetic force works, it stays mutually perpendicular to V and B. If I just look at V, this is the situation I come up with. Now, you have seen something similar in physics 1. You saw a system in which the applied force on a moving object was always perpendicular to the velocity of the object. Let me remind you what the resultant trajectory of that object looks like, right? You have this situation where you get uniform circular motion. It's probably uniform, because you tied a string to something and you're whirling it around your head, and you found that the tension was always in this direction, but the velocity was always perpendicular. So no matter how this thing turned, the tension force remained orthogonal to the velocity vector. That gives you a little bit of clue of what's probably going to happen here. If I have a uniform field and I send in a charged particle at a particular velocity, it's going to start to exhibit uniform circular motion. There are other options, of course. It could exhibit helical motion if I have a velocity in the right direction. We'll see a diagram of that in a second. But we should expect some sort of uniform circular motion to come out of this, and that's because of this weird thing where the force is always exerted at right angles to both the velocity and the magnetic field.